Hey. Full screen. Share screen. Elementary algebra. We have Geo out there in the audience. Welcome, Geo. Who else is here? Nando, what's up, Nando? It's 2 o'clock and we have 3 of us. Let's wait a couple of minutes, see if anybody else pops in. That's long enough. All right, elementary algebra. It's elementary, my dear. So let's look at this exam here. Move number 2 down here. I ordered a new iPad. I'm hoping it comes in soon. With that, I think I might be able to connect to that thing wirelessly, and then I can walk around the room like y'all do the problems for me. All right, so number 1A, we want to go from 17 kilometers to meters. All right, and any of y'all remember that sentence we were supposed to remember last time that gives us the chart? Boys eat donuts, girls. Kids. Yeah, let's see if we can remember this. I know kilometers. I know the middle one is U for units, right? Until mom, millimeter, no, millimeter, till dad tells mom. Millimeter would be down here. Kilometer, millimeter. I know there's centimeter, right? What's the next one? Well, the units are either grams, meters, or liters. Okay. So let's see here. Maisha, welcome, Maisha.
Hey, how you doing?
Okay. All right, Zoe says she's on her way. So Zoe should remember, all right? What is it? These are metric prefixes. My brain's not working well today. So giga, mega, yeah. They don't give us all of them either. They only give us a few. Because there's giga, mega after kilo. So this actually keeps going to the left and the right. They only gave us the first like 3. There was donuts in here, right? Kids wouldn't be eat donuts, would it? E? I don't remember anything starting with an E. Have? Yeah. So this is kilo, hecto, deca, centi. And then we have milli. Well, this list doesn't have one in between. So until dad calls mom. This was these both started with a D, but I can't remember which one it is.
It's a B because it's like right on top.
Deci. Yeah, there we go.
I was like 9, 10.
So milli was 0.001. This is 0.01, and this is 0.1. So this would be 10, 100, 1,000. Hey, we needed you. We couldn't remember our mnemonic. What is it? It's kids. Kids have donuts until dad calls mom. That's what it is. All right. Now we're all here. 1, 2, 3, 4. And we have 5, 6, 7. 7 out of 9. That's pretty good. The other two are doing asynchronous learning by watching YouTube videos later. So we want to go from 17 kilometers to meters. So the way we used that chart before is we're like, okay, here's kilometers, and we go to our unit of meters. 1, 2, 3. So move the decimal to the right 3 times. So we would just say, move the decimal to the right 3 times. That's how many meters it would be. All right, I prefer to use the Smart One method, where I say there are 1,000 meters in 1 kilometer. So the kilometers cancel, and we're left with meters. So it's the same thing as moving the decimal to the right 3 times. Okay.
The way you're doing it right now, like I can understand because like with like the way you're doing this moment, I'm like so confused right now.
That's good, because this chart only works for these. There's actually more. It keeps going. Once you have milli, you also have it goes all the way down to femto, which is like 0.0000000. There's 15 zeros or 16 zeros and then a 1. So there's a lot more prefixes, like over here we have kilo, like what is it? We have kilobytes, megabytes. Where's mega on here? Well, it's over here somewhere, and then you got giga, and tera and so on. So these mnemonics, they're great, but they only work in that particular case. And then, so without understanding, the understanding works in all of these cases, and all the rest of them they didn't put on the chart. You see? Because I mean, if you're just going to memorize this to get the answer without understanding it, why not just use your phone and type in convert this to that? That's easier than memorizing this. You're going to forget this sentence, you're not going to forget how to use Google. But this understanding here is useful for any kind of unit conversions, Like if you end up in a foreign country and you're trying to convert your currency and your cell phone doesn't have service because you didn't switch over to that country's service plan, then you can't Google. But you could still do the math. All right, let's look at B here. So we want to go from 2,000 meters to centimeters. So we're going from meters, our unit of meters, to centimeters. So let's move the decimal to the right twice. So that would be, we moved it to the right twice, we get 2 more zeros, one like that. All right, boom, boom. So let's use our more sophisticated method. In this case, I know I want to get rid of meters. I want centimeters. I know it takes 100 centimeters to make a meter. So we're effectively moving the decimal to the right twice. And now for part C here, okay, we want to go 4,001 centimeters to meters. So we're going from centimeters to the unit of meters. So move the decimal to the left twice. So if we did that, we would have 40.01 meters. If we do it our way, we would say, get rid of centimeters, we want meters. 1 meter is 100 centimeters. So dividing by 100 is effectively moving the decimal to the left twice. Now for number 2. These down here. So A, we have 1,567 centimeters, and we want to go to kilometers. So we go centimeters to kilometers. So that's 1, 2, 3, 5. Thank you. 5 to the left. So if we did that, we would get that, right? 1, 2, 3, 4, 5. Yeah. So to do it using the conversion, this one's a little trickier because I don't know how many centimeters are in a kilometer. I'm gonna have to do two smart ones. I know how many centimeters are in a meter, and then I know how many meters are in a kilometer. So you see the centimeters go away, the meters go away, and left with kilometers. I know 1 meter is 100 centimeters, and I know 1 kilometer is 1,000 meters. All right, so I'm dividing by 1, 2, 3, 4, 5, 5 zeros down there, right? So that's effectively moving the decimal to the left 5 times, just like our little chart says. So B here, we have, make sure I'm recording. Okay, good. 1,700 milliliters. So we're going now, instead of meters, we're talking about liters. All right. So up here, our unit is liters. Remember, you can have grams, meters, or liters. Those are the 3 basic units. So we're going what? Milliliters to kiloliters. All right. Yeah. So here's milli. 1, 2, 3, 4, 5, 6. Gotta move it 6 times to the left. So if we did that, we would have 0.0017. All right, 1, 2, 3, 4, 5, 6. Wait. Yeah, so we need to put 2 zeros before this guy. And we could put these 2 zeros here, right? But those are meaningless, right? If I did this, so we don't really have to put these zeros over there. This would be kiloliters. So to do this the other way, again, I'm gonna have to, yeah, we get rid of milliliters for liters, because I don't know how many milliliters are in a kiloliter. I just know there's 1,000 milliliters in a liter. And then now I have liters, but I need kiloliters. So I'll get rid of liters for kiloliters. And I know it takes 1,000 liters to make 1 kiloliter. So dividing by 1,000 twice, there's 6 zeros down there. So that's effectively moving the decimal to the left 6 times. And now kilograms to milligrams. So kilo, 1, 2, 3, 4, 5, 6. So move the decimal to the right 6 times. We need 5 zeros. Is that right? 1, 2, 3, 4, 5, 6. Yeah. Milligrams. But to do it with the smart ones, I don't know how many milligrams are in a kilogram, but I do know how many grams are in a kilogram. And then I know how many milligrams are in a gram. So the kilograms go away, the grams go away. I know it takes 1,000 grams to make a kilogram. And I know it takes 1,000 milligrams to make a gram. So if I'm multiplying this by 1,000 twice, there's 6 zeros there. So I'm moving the decimal to the right 6 times. Boom, exam is done. Any questions? Okay. So that means we are moving on. We find, no, I don't want that. So syllabus here. We finished 8.2. So we're now in 10.6 is where we need to go in Alex. .6. Right. I already forgot. 10.6 is where we're going. All right. Do, 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 do. So I think we're on course here. I think we have 9 more sections in the book to cover. We have, I think, 9 more classes, so something like that.
Final exam.
I don't remember off the top of my head. I sent an email out and it is in the syllabus here. Here, we could take a look real quick. Okay. No, that's not it. This one. So yeah, up here, final exam, Tuesday, May 10th from 2 to 4:45. And you can zoom in if y'all want. And I'll make the Zoom link later. It'll be on everything we've covered, really. It won't be through Alex. I'll give you 10 problems here from here, but again, you can zoom in. Just like we do the exams, I'll give you 11 problems and each one's worth 10 points. So you can get up to 110. And I'll basically present one problem. It might have several small parts, you know, and you'll have like 15 minutes to work on it. And then I'll show the next problem. And then like there'll be extra time once we've gone through all 11. There's still like an hour left. So if you need for me to go back to one of the problems, like if you didn't finish them or whatever, even if we go back to them. But at the beginning of the exam, I will post the exam online so you can just download it. So if you finish a problem before that 15 minutes is up, you can just keep moving on to the next ones, you know, at your own pace. All right. So don't let me go past 10.6 because from there we got to go to chapter 13. All right. A snapshot of this guy. Bum, bum, bum. So there's 2 parts in 10.6. We're talking about geometry here. Use this arrow. Oops. Oops. Okay. She's got a video. Let's see if it'll play for us today.
To find the perimeter of a triangle, we add the lengths of the sides. As a formula, we can represent this as P equals A plus B plus C, where A, B, and C are the lengths of the sides. Notice that the variable P is isolated, and I can substitute 5 inches for A, 6 inches for B, and 8 inches for C. This gives us the perimeter of 19 inches. So what if we already knew the perimeter of a triangle? Say we have a perimeter of 32 inches. Furthermore, if the lengths of 2 sides are known, we should be able to find the length of the third side. In the figure, side B is 10 inches, side C is 15 inches, and side A is unknown. So I want to solve this formula for side A. That is, I want to isolate the variable A. Since the variables B and C are being added to A, I'll reverse this operation and subtract B and C from both sides. I have P minus B minus C equals A plus B plus C minus B minus C. So now we have P minus B minus C equals A. And I'll write the variable A on the left-hand side. So A equals P minus B minus C. So now I'll enter 32 inches for P, 10 inches for B, and 15 inches for C. This gives us A equals 7 inches. So the length of side A is 7 inches. Now I want to point out that the formula A equals P minus B minus C represents the same relationship among the variables as the original formula. All I did was rearrange the formula to solve for a different variable.
All right. So yeah, these are exactly the same statements in mathematics. They're just worded differently, you know? Like this one says, this one is Yoda saying my skin is green. And down here he's saying green my skin is. So it's the same mathematical statement. Okay, a literal equation is an equation that has more than one variable. A formula is a literal equation with a specific application. So we just saw the perimeter of a triangle, P equals A plus B plus C, can be found, or A, B, and C are the lengths of the sides. So we're going to learn how to rewrite formulas to solve for different variables. So in this one, there's 4 different numbers, P, A, B, and C, and this is their relationship. If you know any 3, you can find the 4th. Okay. All right, so this one, they're missing C here, right? So they start off with P equals A plus B plus C, but they basically just move the A and the B to the other side with P so that C is by itself, and you get this. Okay, does that make sense? Yeah. So if you got P equals A plus B plus C, all right, well, you could subtract B and C from both sides, right? And if you did that, you would get P minus B minus C would be equal to A, right? Because those would cancel. If this is that, and then, or if you wanted instead of A, if you wanted B by itself, you could subtract A and C from both sides. P minus A minus C is equal to, those go away, is equal to B. And of course, you can do it the other way. Instead of B, what if you wanted C? Well, you could subtract A and B from both sides. So you have P minus A minus B is equal to C. So you're just shuffling the letters around. So if you know 3 of the numbers, you can always find the 4th. That's all. That's all they're saying. Okay. Now,
In this video, we have the formula V equals IR. We need to rearrange the formula and solve for the variable R.
This is Ohm's law.
That is, instead of having V over here by itself, we want to isolate R.
Voltage equals current times resistance.
Since the variables I and R are being multiplied, we want to reverse this process and divide both sides by I. We have V over I equals IR over I. And this simplifies to V over I equals R. I can rewrite this with a variable R on the left-hand side. R equals V over I. This formula is expressing the same relationship among the variables as the original formula. We've just rearranged the formula to isolate a different variable. So if we're given values for V and I, we can easily find R.
So this one, there's 3 letters. They're numbers. If you know 2 of them, you can find the third. So you can rearrange that however you want. V equals IR, right? This has V by itself. But what if I wanted I by itself? Now I have I equals V over R, all right? What if I wanted R by itself? By both sides by I. R equals V over I. That's it. So voltage equals current times resistance. We'll give a quick tangent on how electricity works. So y'all heard about electrons, right? All right. And protons are positive. So the nucleus of an atom is protons, and then you have these little electrons that bob around. Yeah, you have protons. Let's say you got 3 protons in the nucleus. Well, then typically you have 3 electrons orbiting it. Sometimes you have neutrons, which are neutrally charged. So if you have 3 positives and 3 negatives, overall the atom would be a neutral charge, all right? So so electric charges create electric fields, okay? And you have magnetic fields too, right? You all know about magnetism. Well, you know what light is, you see it every day. Well, microwaves and radio waves, gamma rays, those are all just light, but they have a wavelength that we can't see with our eyes, but it's all just light, okay? Light moves in waves. It's also thought of as a particle. A photon is a single particle of light.
Right, because light waves, like if you have a certain heat wave, you can actually see in the light, and it's really cool. And like I see how it works because it's sort of like air, like it's moving like air.
Yeah, waves are waves. If you think about it as water or anything, you know. So if you have electricity, right? People, you know, like amateur electricians, they think of the wires like a water pipe, and I think like electrons are flowing through the water pipe. That's kind of, it works if you're doing like a wall outlet or whatever, but the way that there's a difference between electric charge and actual energy, right? The way what light actually is, it's a combination of an electric field and a magnetic field. So it turns out if you take an electric charge and if you accelerate it, right, if you move it, then you have a changing electric field because the source of the field is moving. Well, a changing electric field creates a magnetic field. It turns out that electricity and magnetism are the same thing, right? So if that electron is just sitting there, there's just an electric field. But if you're walking by it, it doesn't know that you're walking by it. Relative, to you, it's moving by you. So if you're moving, you see a changing electric field, which is what a magnetic field is. So it's relative, right? A magnetic field is an electric field. It just depends on who's moving. So the other thing is, well, if a changing electric field makes a magnetic field, the same thing goes the way around. A changing magnetic field makes an electric field. right? And so that's what light is. If you think of like light traveling like that way, basically you have a up and down. Here's your electric field. Okay. So it has a certain amplitude. And then at a right angle to that is your magnetic field. So what light is it's a changing electric field that's creating a magnetic field that's changing, thus creating a magnetic field. They're creating one another. That's how it propagates through space. So if the electric field is pointing up and the magnetic field is pointing out at us, the actual energy is going in this direction. All right. So let's say I have a battery. Okay. And right here next to it is a light bulb. Okay. So I'm going to take the wire instead of going straight to it. Okay. So it's both positives and negatives. All right. And let's say that this wire is so long, it goes like to the other end of the, well, halfway to the end of the galaxy and back. Let's say that this wire is so long, it would take light 1 second to go all the way from the battery to the bulb. So the question is as soon as you flip the switch, does it take 1 second for the light to turn on, or does it turn on instantaneously? Because remember, light can only go at the speed of light. Nothing can go faster than that. So if the power is going all the way through the wire from the battery to the bulb, which is right next to it, it would take 1 second, right? If let's say the electrons in the wire were moving in the wire and the electrons had to go all the way from the battery to the light and they moved at the speed of light, it would take 1 whole second for the light to turn on. But that's not how electricity actually works. There's direct current, but what we use is alternating current. The electrons in this wire are barely even moving. They just barely move right and left. That's it, just a tiny little amount, just barely move. And somehow we get all this electricity. Well, it turns out that although the electrons are just bobbing back and forth, just barely, that's all they're doing. They don't actually go anywhere. They go one way and then they go right back to where they were. So how is that giving energy to this light bulb to turn it on? Well, everywhere along this wire, you have an electric field because there's electrons and they're moving, just barely moving. So it's creating a magnetic field, right? So if the electric field is going up and down and the magnetic field is going this way and this way, it turns out that the actual energy itself is traveling. As soon as you flip this switch, the energy is going straight from everywhere the electrons are moving to the light bulb. So the light bulb would turn on basically instantly. So the energy isn't going through the wire at all. For my laptop to be running right now, it's actually all the way from the power plant through the power lines and everywhere, from every point in space, from all those places, light is shining from the power plant directly to my laptop. From this cord right here, light is shining directly from here to my laptop. The power lines out there that lead up to this, the light is shining directly from the power lines to my laptop to power it. So power doesn't travel through the cables at all. It's traveling through space. Well, it's just traveling through space is how electricity actually works, which most electricians have no idea that that's the actual physics of it, because it's bizarre, right? This is why Tesla was trying to create a worldwide network where everywhere on the earth, you just had wireless electricity, as well as telecommunications, right? We get our cell phone signal wirelessly, right? Well, that's, just waves of energy. It's all light. So he wanted to have free electricity for everyone, as well as free communications globally.
Which is really cool because like the communication, before they didn't know how to make it into like magnetic wave things to help connect you from one side of the planet to all the way to the other.
Mm-hmm.
Someone finally cracked the code to do that.
Let's look at an example here. We'll do a perimeter example real quick. So there's two kind of approaches here. We have P equals A plus B plus C, right? Now, we know A and B, we don't know C. Okay, and we know P is 20. So one approach is plug the numbers in and then solve. So if we replace P with 20 feet, replace A with 5 feet, replace B with 7 feet, and then we have C, right? But we could simplify this. We have 20 feet is 12 feet plus C, right? Then we could subtract 12 feet from both sides. And over here we have 8 feet equals C. Right, that's how most people, when they first start trying to do problems like this, they plug the numbers in first. And you can do that,
That's how I do it.
but it's typically more elegant to work with the letters first, get your letters the way they want, and then plug the numbers in. So if you're looking for C, right here, what you'd want to do is subtract A and subtract B from both sides. And you get P minus A minus B is equal to C. And now you plug in your numbers. So you'd have 20 minus 5 minus 7 equals C. And we're talking about feet here. So 20 minus 5 minus 7 gives us 8. In this case, feet. So typically you want to work with the algebra first. And then the last step is plug the numbers in. And a lot of problems, you'll see why, because the numbers get nasty. You get the same answer either way, but typically working with the letters first is a lot simpler than plugging the numbers in first. Okay.
Because it's confusing when they use the letters, like they're like, oh, I don't know how to do it, and like I tell them how like need strikes and like it's good for you, but like I just say try it. I think when I'm doing the math problem, the algebra math problem, and it has like X, Y, or something, I thought that out mentally.
You try to get rid of all the letters and replace them with numbers, right? That's just a way of trying to avoid doing algebra, right? You try to do more arithmetic, less algebra. The algebra is the tool, right? You want to manipulate the letters and put the numbers in last.
The letters are confusing when it's in the problem for most people. They get the wrong answer.
They're only confusing if you don't know algebra, but the point here is to learn algebra, not avoid learning it. So use the letters.
I still write it down, but I just mentally thought it up.
Well, just remember the letters represent numbers, right? What if the numbers are 17,796,142 and all the other letters represent huge, ugly numbers or giant piles of fractions? You don't want to deal with all that. You don't want to be writing those numbers over and over and over again. It's a lot easier to write the letter A. And then at the last step, then you plug the numbers in, right? So yeah, your method works great if you're only dealing with numbers like 1, 2, and 3. But in the real world, numbers are ugly, very, very ugly. And you don't want to have to write them over and over again. All right, so that's one reason why you want to manipulate the letters first. So they want us to solve for t here. So they're multiplying the t by an r. So if we just divide both sides by r, you could see that t is d over r. Then whatever d and r are, you plug those numbers in and you have t. Here we want a y, right? So to get y by itself, the first step is let's get rid of that. So we subtract 5x from both sides. And if you do that, you get 2y equals 12 minus 5x. But now there's this 2 here. So we get rid of that. We have to divide both sides. Notice over here, I divided the whole thing by 2. So those go away. And I have y equals 12 minus 5x over 2. which we could simplify if we wanted to. This is 12 over 2 minus 5 over 2x, just separating that. 12 over 2 is 6. So this is a chain equality, but we have y equals 6 minus 5 halves x. These are both correct. It just depends on how you want it in the end, okay? Those are both correct. Just two different ways of writing the same thing. Typically, you want it this way for reasons I won't go into. Okay? So let's learn about avoiding mistakes. It says manipulate the letters first and then plug in the numbers. All right, it says in the expression negative 5x plus 12, do not try to divide the 2 into the 12. The divisor of 2 is dividing the entire quantity, not just the 12. All right, so what they're saying here is what I just said. You have to divide everything by 2, not just the 12. Okay. All right, if we want the L, divide by the W, yeah. So we see that L is A over W. And A equals LW. You should be able to look at this and be like, oh, what am I looking for? W? I could just go, boop. All right, that's what you want to see visually. All right. Or if I wanted W, just dump. Okay. So here we want A. So let's get this off of our thing that has the A in it first. We'll subtract 4B from both sides. So what we get is negative 2A equals 7 minus 4B. So now to get the A by itself, we'll divide everything by a negative 2. So we have 7 over negative 2 minus 4B over negative 2. So this would be a negative 7 halves. We have a minus over a minus. All right. And then a 4 over 2 is 2. So just simplifying there. Yeah, I know some of y'all have to ditch out early. I'm going to throw the exam in real quick. I'll bring it back at the end of class. Exam number 18, I believe. Okay, let's see. Oh, I forgot the quiz, didn't I? All right, well, I'll throw down the exam and then we're going to do the quiz since I forgot to do the quiz. So we'll solve for X. Let's see. 2x plus A minus B equals C. Number 2, 3x y minus z equals 2a plus b. This is a 2. And I'll do it. There. Now we know exactly what it is. My z's have a line through.
I do the Z like that, and then like do the Z like myself. It doesn't really look like it, but when I embrace it and I do like first and two.
So since I forgot the exam, I'm gonna put, I forgot the quiz. Let's do the quiz that I totally forgot to do. Quiz number 18. All right. 1. Solve for x. Let's see, I do 2x, y, z plus a equals b minus c. And x over 2 plus y minus z equals a over b. You got the basic principles. X is going to be equal to a big pile of stuff that has a's and b's and z's and whatever in it. Okay. So we'll take 15 minutes to play with these. Let's see, it's 250, so it'll be 305. At 305, we'll whatever, 305, we'll work the quiz together. So out there in Zoom land, I'll put you all in a breakout room. Okay, so for number 1, we're trying to get to this x here, right? So we got to deal with this and this and the a. And we want to get all that off of its back. So let's start with this guy, and then we'll deal with this pile of stuff. So we'll say, we got this. So to get rid of that a, we'll subtract a from both sides. All right, so that goes away. Now we want this by itself, but we got this and this in the way, right? My 2xy b minus. So all I did was rewrite the same thing. So to get rid of these things, I want to get rid of that 2. I want to get rid of the y, and I want to get rid of the z. But whatever I do to this side, I have to also do to this side. Right, the 2. Okay, so the 2's go away, the y's go away, the z's go away. I'm left with my x. And it's equal to b minus c minus a all over 2yz. So that's one way. Here's another approach. All right. Let's say, or I'm going to start off with this. So this method, I was like, I'm going to get rid of the a first. What if I try to get rid of this stuff first and then deal with the a second? Well, if I was going to do that, I can't just divide this thing by, I can't just go 2yz like I did over here. I'd have to do this to the whole side. You see what I mean? You have to do it to the entire side. And if I did that, all right, over here, I'd have to separate this. This would be a 2xyz plus a. And they're both over a 2yz. And I have a b minus c over a 2yz. So yeah, that goes away, that goes away. And I have this x, but now I have an a over 2yz. So now to get rid of that, I'd have to subtract a over 2yz from both sides. So that cancels that. And now I have x equals, oh, I forgot my minus a over 2yz. You have to subtract that from both sides of the equation. So luckily there is a common denominator of a 2yz. So I can combine those. I would get B minus C minus A over 2YZ. So you see how ugly this approach is, right? Yeah, that's why you want to deal with the A first. It makes things a lot easier. Because remember, like if your order of operations, you multiply things and then add them. We're doing the opposite. We're going backwards. We're trying to undo what's been done to the X. All right. So the last thing they did to X was to add this A. First, they multiplied by 2, they multiplied it by Y, they multiplied it by Z, and then they took that quantity and added A. So if we're going to undo what's been done to X, we want to do what they did, but in opposite order, in the opposite operations, okay? So this is better approach. Okay, approach, okay? So this works, right? We get the same thing, but man, it's a big pain in the butt, right? Let's look at number 2 here. So solving for X. So again, there's that 2 there, but really let's get rid of this first, okay? So I have this X over 2 plus Y minus Z and A over B. So I want to get rid of this Y, so I will subtract Y from both sides. I also want to get rid of this negative Z, so I'll add Z to both sides. So that cancels and that cancels, okay? So what you can kind of see is all we've done was taken the Y and we moved it over here, all right? So if it's positive on this side, I move it over here, it becomes negative. And the Z, I move over here and it's negative here, so when it goes over there, it's positive, okay? You're just moving the Y and the Z from the left side to the right side. So now we have this X over 2 equals big pile of stuff. All right, so now I got to get rid of this 2. So what I need to do is I'll multiply both sides by 2. You got to do the entire side, okay? So if I do that, that goes away and I have X equals. Now when you have something like that, you have to distribute. You have to multiply everything in here by 2. So when you do that, you get a 2A over B. And you do the 2 there. And we have a minus a 2Y. Let me fix my 2's here so I don't mistake them. And then we have a 2 times a Z. And that's it. Let's look and see what it looks like the ugly way. Or if I took this and let's say I multiplied both sides by 2 first. Then what we get is the 2 times the X over 2 gives us an X. And we get a 2Y. Then a minus a 2Z equals A times 2 is the same as 2A. All right. So from here, I want to get the X by itself. So I'm kind of running out of room here. To get rid of that, I subtract 2Y from both sides. And then to get rid of this, I'd add 2Z to both sides. So that would cancel that, that would cancel that. Now we have the X by itself. What do I have over here? I have a 2A over B minus a 2Y plus a 2Z. The same thing we have here. It's just this is a lot uglier, right? Okay. So this is the easier approach. So if you have your X, deal with whatever's being added or subtracted first, and then deal with the multiplication next. All right, so there's the quiz. Sorry, I forgot to do that at the beginning of class. I remembered to, yeah. All right, so now moving on. Again, we'll come back to the exam later. Where were we? Did we do that one yet? We haven't done this one yet, the skill practice, right? I guess we did do that. Yeah. All right, let's see what this lady has to say.
In this video, we have the equation 3x plus 4y equals 8, and we need to solve for y. That is, we want to isolate the y variable. So first I want to isolate the term containing y. So if I add the opposite of 3x to both sides, that will remove the term 3x on the left. We have 3x plus negative 3x plus 4y equals negative 3x plus 8. Notice that on the right-hand side, I wrote the negative 3x term first, in front of the constant term. I did this because it's conventional to write the variable terms first, followed by constant terms. That being said, if you wrote this as 8 plus negative 3x, that would also be completely correct. Simplifying, I have 4y equals negative 3x plus 8. At this point, I want to get a coefficient of 1 on the y term. So I'll divide both sides by 4. Notice that the division bar on the right extends over both terms, negative 3x and 8. That is, both terms are being divided by 4. So we have y equals negative 3x plus 8 all over 4. Now we're actually done. We've isolated the y variable, but you might be tempted to try to cancel the 8 and the 4 here. We're not allowed to do that because the 4 in the denominator is actually dividing into both terms in the numerator. So I can't just strike through the 8 and the 4 because the 4 is also dividing into the term negative 3x. So instead, what we can do is rewrite this as y equals negative 3x over 4 plus 8 over 4. In other words, I've written the big fraction as two separate fractions, and in each case, the division by 4 is maintained. This now simplifies as y equals negative 3/4 x plus 2. So we actually have two ways we can express the final answer, and both are correct.
All right, so both of those are the same thing. All they're doing is separating the fraction. You got the minus 3x, it's over 4, and then the plus 8, it's also over 4. So they're just separating it. 8 over 4 is 2. See, 8 over 4 is the same thing as 2. Remember, adding fractions here, we're just separating them. Okay. Celsius. So she is talking about putting it in the form of y equals mx plus b. So all they're saying here, ax plus by Forgot what I was looking at. Oh, by equals c. So here, the a's and the b's are numbers, the x's and y's are variables. So think about like 2x plus 3y equals 4. That's an equation in two variables, x and a y. It's 2 dimensions of space. If you graphed it, it would be a line. What if we had 6x plus 3 plus 4y equals 7? That's another equation, two variables, right? Well, every single equation of two variables could be put in this form. So this is to talk about an infinite number of equations, right? So yeah, y'all don't like the letters. Here we have letters that represent numbers. These are variables. But now we want to talk about classes of equations. So these would be like parameters, the a's and the b's and the c's, where the x's are your variables. So every single one of these I can solve for x, okay? So instead of doing every one of these separately, why not do them all at once with this guy? You see, if I took this, let me break it down step by step the way y'all should do it. Let's say I subtracted by from both sides. So now I got an ax equals c minus b. Actually, never mind, we're trying to solve for y, not x. So if we want y, here's y. We take away the ax from both sides. So that goes away. Now we have by equals, I'm going to put the x part first. I'm going to put this before that. Because what we're looking for is something in this form, y equals mx plus b. So x and y, m and b are just whatever. So now to get y by itself, we divide by b. So we have y. Great. All right, and if we separate this, we get negative a over b x plus c over b. All right, so every single one of these equations, if you're solving for y, it's always going to be this. Just plug in your a and your b and your c. Why they say we're aiming for this form, this has the same form. M is the minus a over b, and the lowercase b would be the capital C over b. You'd have the two letters and then the number. So we just solved an infinite number of equations that are all in this form. You got an x and a y and then a number by itself. All right. So that's why we like to put things in this form, because then it's easy to graph it. You see, if you have if you have an x and a y axis, right? If you have y equals mx plus b here, all right, the x is left and right, the y is up and down. If you look at all the solutions, a solution to this equation, what if I had like y equals 2x plus 1? A solution to this equation requires two numbers, an x and a y. Y'all are used to just having an x, right? Like x plus 1 equals 2. That has a solution 1. 1 plus 1 is 2. Well, this has two variables, so a solution to that, you'd need two numbers. So if let's say I put in minus 1 for x here, 2 times minus 1 is a negative 2, plus 1 is a negative 1, so I'd have to have a minus 1 there. So negative 1, and so a solution to something like that has two numbers. So if I went back 1 and down 1, that would be a point on a line. So the set of all the solutions to this, there'd be an infinite number of sets of solutions, and each one has two numbers. And if I graph them all, I would get a line. Okay, so this first number tells you the slope, which means if it's positive, you're going up. If it was a negative number, you'd be going down. And then this number, well, what does it tell you? Y equals mx plus b. If I made x 0, that goes away, and I have y equals b. So when x is 0, that means I don't go right or left. Then the y is just this number. So this would be B. So basically you have a line right there where it crosses the y-axis. That's the B number. All right. And then this tells you the slope. So that would be your change in y over your change. They call it the rise over the run. So if this is 1, that's like a 45-degree angle. If it's bigger than 1, it's more of a slope. If it's negative, it's downhill. So that's why we like to take these equations that look like this. If we manipulate them and make them look like this, then we can instantly see a picture in our head of the line. We know how far it's, because every line starts off like this, and then either you tilt it upward or you tilt it downward. All right, or I should say you start with this, then you either tilt it up or you tilt it down. So let's say I tilted it up, I'd have this, and then you can move it up and move it down. So that's what this is doing. This is the tilt, and then this is the shift up or down. But whenever it's written like this, instead, it's like, I don't know what that looks like. So we always want to take it and make it look like mx plus b, because then you can see, oh, here's the tilt, and then here's the shift. And then you can quickly just see it. So that's the purpose of all that. Anyhow, the formula C equals 5/9 times F minus 32 is used to find the temperature C in degrees Celsius for a given temperature in degrees Fahrenheit. So solve the formula for F. So let's say we're used to Fahrenheit, right? But they've given you the temperature in Celsius. You're like, it sucks. Well, I have a formula. Well, this works if I knew the Fahrenheit, I could find the Celsius, right? I want the other way around. You know, I want to plug in the Celsius and find out what it is in Fahrenheit so I can make sense of it. So we need to rearrange this guy here. So I want to get the F by itself. Okay. So the first thing I'll do is I'm going to get rid of that. And I'm going to do that by dividing by 5 and multiplying by 9. Now I have to do this to both sides. And I did that because the 5s go away, the 9s go away. You see there? So now I'm left with 9/5 Celsius is F minus 32. So now to get F by itself, I'll just add 32 to both sides. So I get 9/5 degrees Celsius plus 32 is Fahrenheit. So now since they say, here's the temperature, it's in degrees Celsius, I'm like, what? I just take that temperature and multiply it by 9, divide by 5, and then add 32, and then I have the temperature in Fahrenheit. All right, so let's look at this one. Okay, so we want to get the X by itself. So we have Y equals 1/3 X minus 7. So what I'm going to do is get rid of this first by multiplying both sides by 3. So now I have a 3y equals X minus 7. Now I can just add 7 to both sides. So I get a 3y plus 7 equals X. Okay, I got all kinds of stuff here. Our videos are so boring. I don't want us to get behind here. Okay. So here they say the length of a rectangular lot. So first thing you want to do is draw a picture. Okay. They say the length is 1 meter less than twice the width. So let's use L and W, right? So if the length is 1 meter less than twice the width, so we're talking about the length is 1 less than twice the width. So if we take twice the width and subtract 1, that gives us the length. So these things, when they say it in words, it's kind of awkward and you have to really think about it. It's like, okay, 1 less than twice the width. That's what the length is. The length is 1 less than twice the width. All right, they say the perimeter is 190. Okay, so I'm going to say P is 190. Find the length and the width. All right, we're going to need more space here. So these are the two things they've told us. All right, well, I know the perimeter, if this is the length, that would be the length, this is the width, the width. The perimeter is twice the width plus twice the length, because you have this side, this side, this side, and this side. So the perimeter would be 2W plus 2L. Okay. So they don't tell you that, but you should be able to figure that out from the drawing, right? So now we have these two equations. We have two equations and we need to find two unknowns, L and W. So we have this one and we have this one. Okay, so what we can do here is substitute. If you have two equations, you can solve for two unknowns, but look, you can't get just L or W over here, and over here you can't either. So you have numbers, but what we can do is if we take this is L, right? Let's plop it in right there for L. So if we substitute, what we get here is we have 190 equals 2 W plus 2. Now L, this L here, boop. L is the same thing as 2W minus 1. I substituted. I got rid of L and rewrote it in terms of W. So this thing right here, there's two letters. There's W and the L. But now since I have L in terms of W, I plug it in there. Now look at this. There's only W's. There is no L. Neat trick, right? So now I can solve for W. I'd have 190. I got 2W. If I multiply this through, I get a 4W and a minus 2. So if I combine these like terms, I got that. Now I can add 2 to both sides. So I got a 192 is 6W. Now I can divide both sides by 6. And whatever 192 divided by 6 is, 192 divided by 6 is 32. All right. Now I know what W is. And now I could take this and go back up here. If I know what W is, I can find out what L is. See what I mean? So let's do that. L is twice W. Well, W is 32. So we take twice 32, subtract 1. So this would be 64 minus 1, which is 63. So the whole trick here is when you have two unknown quantities, you need two independent equations. And the trick is use one and substitute it into the other. So we're rewriting L in terms of W. We just replaced L with this expression in W's. And then we only have W's now. And then we can use our algebra to solve for W. We get an actual number. Then you go back to that original equation. Since you know W, you plug it in here and you can get L. Sum of the angles in a triangle. All right. The angles in a triangle always add up to 180 degrees, as long as it's drawn on a flat surface. If it's drawn on a sphere, they add up to more than 180 degrees. Okay, so let's do well, here's another example. The length of a rectangle is 10 feet less than twice the width. So the length is 10 less than twice the width. So you take twice the width, take 10 away from it. They say the perimeter is 178 feet. Well, again, we have a length, width. So here they say 178 is the perimeter. Well, the perimeter would be twice the width plus twice the length. We're just adding up all the sides. So here's our two equations. Okay, and we could solve that in the same way we did the last one. Let me put them side by side here. So here's our two independent equations. Boom. There's two unknowns. So what we'll do is we'll take L here. And we'll plug it in. We'll take this and we'll cram it right there. So if we do that, we get this new equation. And now we only have W. So if we solve for W now, we'll multiply this out. 2 times 2 is 4. 2 times 10 is 20. 2W and 4W make 6 W's. From here, we can add 20 to both sides. So we get a 198 equals 6W. Now we'll divide both sides by 6. So 198 divided by 6. It's 33. So now we know that W is 33. We could plug it in right there. We could say 2 times 33 minus 10. This would be 66 minus 10 or 56. That's what L is. So substitution. And now we're going to talk about triangles. Two angles are complementary if their sum is 90 degrees. So let's say this is 90 degrees right here. This angle and that angle are called complementary because they add up to 90 degrees. All right. Supplementary if they add up to 180 degrees. So from here to here is 180 degrees. So this angle and this angle would be supplementary because they add up to 180. The sum of the measure the angles in a triangle is 180 degrees. So if I have a triangle, say I'll call that alpha, beta, gamma. Alpha plus beta plus gamma is 180 degrees. And that's always true of any triangle drawn on a flat surface. If it's on a sphere, if you have a curved surface, the angles will add up to more than 180 degrees. And that's actually how we figure out how curved something is. So we use that in space to test general relativity. If you shoot lasers, light goes in a straight line, right? But it's hyperbolic geometry. So if we made a big enough triangle in space and shot lasers and then looked at the angles, right, we'd be able to tell if the universe is actually a 4-dimensional sphere instead of a 4-dimensional flat space. So we can actually tell the curvature of the universe itself. Just like we live on the surface of the earth, it looks flat to us, right? But it's actually the surface of a 3-dimensional sphere. Okay? The measure of vertical angles are equal. I don't know what that means. Vertical angles. I don't know, maybe we'll figure that out. Vertical angles. I don't remember what they mean by that. Let's look at this example. All right, so here we have a 90-degree angle. We usually use a little box to represent a 90-degree angle. So these are complementary because if you add this to this, you're going to get 90 degrees. All right, so to say that, we'd say 7x plus 4, that many degrees, plus x degrees is equal to 90 degrees. Since we're talking about everything's degrees here, I'm just going to write 7x plus 4 plus x is 90. We know we're talking about degrees. All right, so in this case, we can find out what x is. 7x and an x give us 8x. Now we can subtract 4 from both sides. So we got 8x equals 86. Now divide both sides by 8. And whatever 86 divided by 8 is 10.75. We're talking about degrees here. So again, in geometry, this plus this is 90. That's the basic formula. All right, two complementary angles are constructed. So remember, complementary means they add up to 180 degrees. So if this is alpha and this is beta, alpha plus beta are 180 degrees. So they are drawing them so that one is 1 degree less than 6 times the other. So I'll call them alpha and beta. Alpha is 1 degree less than 6 times the other. So that's our equation. We have alpha is 1 degree less than 6 times the other. So this is our equation. So we have I'll just call them alpha and beta. All right, the diagram's not to scale, all right? But we know that alpha here is 6 beta minus 1. All right, so because these add up to 180 degrees, all right, we could say alpha is 6 beta minus 1. So we're going to replace alpha with 6 beta minus 1. And we still have our plus beta. This is equal to 180. So 6 beta and a beta give us 7 betas. Now we can add 1 to both sides. We have 7 beta is 181. Now divide by 7. So whatever 181 divided by 7 is, 181 divided by 7 is 25.86. In this case, degrees. So we're using this and this. So again, we have 2 equations, 2 unknowns. We're substituting, we're getting rid of beta in terms of alpha. Once we know what beta is, we can plug it in here and figure out what alpha is. Okay, one angle in a triangle is twice as large as the smallest angle. The third angle is 10 degrees more than 7 times the smallest angle. All right, so let's draw this. We have alpha, beta, gamma. So let's say one angle, I'll call it alpha, is twice as large as the smallest angle. So I'm going to say that beta is the smallest. So alpha is twice as big as the other angle. So that's that statement. Now they say the third angle. So now we're going to talk about gamma. It is 10 degrees more than 7 times the smallest angle. So we called the smallest angle, we said that's going to be beta. So this is take 7 times the smallest angle and then add 10 to it. So we have these two equations and we want to solve for all three. Well, there's 3 numbers here, alpha, beta, and gamma, but we only have 2 equations. The other equation is if we add up the angles, we should get 180 degrees. So now I have 3 equations and 3 unknowns. So the way we do that is the same way we did the others. We substitute. So what we want to get is one equation with just one letter in it. So the way we're going to do that is, let's see. This has 3 letters, this one has 2, this one has 2. So how can we get one equation with just one letter by substituting stuff in? What we can do is, this has alpha, beta, gamma. Let's say I took this and plugged it in here. So if I replaced gamma with this, now I just have beta and beta, but here's an alpha, right? But here's alpha in terms of beta. So what if I did that? So if I replaced alpha here with 2 beta, and I still got that plus of beta, and then I replaced the gamma with this, I just made a new equation and there's only the letter beta in it. Neat trick, right? So yeah, alpha can be written in terms of beta, gamma can be written in terms of beta. So I just substitute those in, boop, boop, and now I have this thing with only betas. So this thing tells me, well, 2 beta plus a beta is 3 beta plus 7 beta. That gives me 10 betas. And then I still have my plus 10 here equals 180. So now I can subtract 10 from both sides and I got 10 beta is 170. Now I can divide both sides by 10 and I have beta is 17. Now that I know what beta is, I can go up here, I can put it right here. So alpha is 2 times 17, which is 34. Forgot my degrees here. So now I know that alpha is 34. Gamma is 7 times beta plus 10. So I could say, since beta is 17 plus 10, that's 7 times 17. 7 times 17 plus 10, that's 129 degrees. So now I know alpha, beta, and gamma. And it all came from these 3 equations. And I just substituted one into the other to make an equation with only one variable. All right, in a triangle, the measure of the first angle is 80 degrees greater than the measure of the second angle. Okay, so we got alpha, beta, and gamma again. We need more. So the measure of the first angle, we'll call that alpha. It is 80 degrees greater than the measure of the second. So we take the second and add 80. All right. So 80 degrees bigger than the second, it gives us the first. The measure of the third angle, that one's gamma, is twice that of the second. So find the measures of the angles. I'm going to leave off the degrees. We know we're working with degrees, right? So those are two equations, but there's three letters. There's three unknowns. We have to also use the fact that all the angles add up to 180 degrees. So there's our three equations, and we have three unknowns. So we need to, let's see, I can rewrite alpha in terms of beta, right? So here's alpha. I can replace it with a beta plus 80. And here's gamma. I can replace it with a 2 beta. So if I do that, if I replace alpha here with beta plus 80, then I got a beta. And then I'll replace gamma with twice beta. So this is a new equation I made from these three by substituting these both in to that third one. So now there's nothing but betas here. So beta plus 2 beta gives us 4 betas. We still got this 80 here. It was 180. I could subtract 80 from both sides. And I got 4 betas is 100. Divide by 4. So beta equals 25. So that tells me that gamma is twice 25, which is 50. I should put my degrees now. And I can also put it right there. Alpha is beta plus 80. So that's 25 plus 80. That's 105 degrees. So now we've solved for all three. Wrong button. The distance around a circular garden is 188.4 feet. Find the radius to the nearest tenth of a foot. So if you have a circle, the radius is the distance from the center to the outer edge, R. The circumference, the circumference or the distance around it, right? To go all the way around it, that's called the circumference. It is 2 pi r. So pi is 3.14 ... Okay. Notice twice the radius would be the diameter, right? So I could also say this is dr. And if I divide both sides by d, pi is the ratio of the circumference to the diameter of any circle. That's where it came from in the very first place. Okay. But here we're working in terms of the radius. So they want us to find the radius. I'll put it, this is a formula we need to remember. We want to find the radius. So if we want to find the radius, we can divide both sides by 2 pi. So we see the radius is the circumference divided by 2 pi. They told us the distance around the garden, that is the circumference, is 188.4 feet. And we have over 2 pi. So if we plug this into our calculator, 188.4 divide by 2, and now divide by pi. On an iPhone, if you turn your calculator sideways, you get extra buttons. And this is 29.98 feet. Hey Hector, how's it going?
Good, how are you?
I'm all right. Yeah.
Yeah, doing Cal 2?
Right. No, elementary algebra today. This is a hard section. We get all these new formulas, you know, with all the geometries. But a lot of my students ditch towards the end of class to avoid traffic, you know.
Oh, okay.
But we only have nine students in here. Yeah.
Still have all 9?
Well, I started with 10 and then I have one. The one of them had already taken the class, so it was in the wrong class. But yeah, they're out there. Some of them are zooming in, and then I got a couple of that. Yeah. And I got a couple of them doing the asynchronous. So they do watch the YouTube video, you know. So for them, I just register. Yeah. Yeah. Full.
That's what happens when you know how to use technology.
Mm-hmm. Well, I just click on Zoom and that's it. You know, it does it for me, you know.
So are they watching you through there or?
Yeah, I got the little
Oh, so
camera.
That's what you have. What we don't.
Yeah, I mean, it's they don't really need it. They don't need to see me at all.
That's true.
So I just put it there for fun. All right, take care. The boss. Yeah. Yeah, he's the department chair. No, that's fine. It's all good. All right, let's see here. He's really, really cool. He's saved me by making sure this class made by moving it here from Kerrville, you know. Otherwise, I wouldn't have had this class to teach. I'd have lost half my income. That would have sucked. So let's look at this one here. So again, the circumference of a drain pipe. So you have a pipe here. So they're talking about the distance around it. All right. Again, circumference is 2 pi r, where r is the radius. So they want us to find the radius. So if we divide both sides by 2 pi, we have r is circumference over 2 pi. So we just plug and chug. We have 12.5 centimeters divided by 2 pi. So if we plug this into our calculator, we have 12.5 divided by 2 divided by pi. We get 1.99 centimeters. Pi on the calculator key. Guess I could throw that in here. So depending on what kind of calculator you're using. All right, it says, yeah, you should use the pi key on your calculator. So they did 188.4 divide by, let's see, that's not how I do it. If you can enter in like parentheses on your calculator, you can do that. So you'd want to have divided by, you want these parentheses here because you're dividing both the 2 and the pi. All right, the way I do it though is I do 188.4, I divide by 2, and then I divide by pi. So what this is I'm not dividing the 2 by pi. It's because the way the calculator works. It's actually this, I'm dividing that by 2, and then I get a number, and now I'm dividing that by pi. Okay. So you want to be careful. Yeah, so here, if you have a graphing calculator, notice they put the parentheses because you want to be dividing by the pi, not just the 2. See this right here, that you're actually multiplying by pi, right? You have the 188. Yeah, they divided by 2, but then that pi there, they're actually, you're multiplying it. So that one, it looks like it's on the bottom of the fraction, but it's not. Be careful there. So yeah, it should make sure you can do these types of problems. So like this 1600 divided by this, let me show you what I would plug in. The order of the buttons that I use on my iPhone because I don't have a graphing calculator. See this, I would do 880, then I'd hit the divide button, hit 2, and then I'd hit the divide button and hit pi. All right. The graphing calculator, you do 880 divided by parenthesis 2 pi. All right, this one I do on my iPhone, I do divide by pi. And then we have 4 squared here, so I just divide by 4 twice. Okay, but if you have a graphing calculator, you would do oh, I missed my. What's that?
So it's 4 squared. So can you do,
Yeah, you could do that instead. You could do like, all right, because 4 times 4 is 16, right? 4. Yeah. Dividing by 4 twice is the same as dividing by 16 once. Yeah, good point. So this one here, I take 20, divide by 5, and I divide by pi. If you have a graphing calculator, you could do that. And this one's the same thing, 10 divide by 7, and then I divide by pi. If you have a graphing calculator, you could actually put parentheses and do that. So iPhone calculator, graphing calculator. That's the whole section. 10.6. All right, we finished 10.6 here. So in which case we can just check out the exam. So that's it for the lecture today. Let's see, Tuesday. We'll see y'all Thursday. I'll be here for a while, so if you want to work the exam in class, you can. How you doing out there, Maisha?
I'm doing good. I'm about to get ready to log off and do this exam and this quiz. And get it done and over with.
All right, well, you followed the quiz, right? You know the first steps here.
Yes.
So here you move the A over, move the B over, and then divide everything by 2. Right?
Yeah.
This one down
All right.
here, move the Z over, and then divide everything by the 3 and the Y. Okay.
Gotcha.
All right.
Thank you.
Sure. Bye.
Mm.